Hey everyone, welcome back and let's write some more neat code today. So today let's solve stickers to spell word. I'm not going to lie, this is a pretty hard problem and we're going to be solving it first. I'm going to show the brute force way and then I'm going to show how we can use memoization, and that's going to give us a more efficient solution, but even this solution is going to be exponential. It's going to be roughly 2 to the power of n, and it's actually going to be even worse than that. But I think even solving this problem in the brute force way is also not super easy. And this problem is pretty similar to the problem word break, which is also a dynamic programming problem. But this problem is kind of like word break on steroids. So this problem is definitely a lot harder. So we're given n different types of stickers. Each sticker is basically a lowercase English word. So in this entire problem, we're going to be dealing with lowercase letters from A to Z. So that's good. It gives us a limit of 26 different types of characters. And we want to be able to spell a certain target string. And we want to be able to spell this string using individual letters from our collection of stickers, right? And if we have a sticker such as, let's say the sticker is with, right? Each sticker is a word. So maybe we need a couple characters from this. Like let's say we take 3 of these characters and use them in target, right? We're allowed to do that, but we don't have to use every single character. So maybe we just don't need to use the W. That's perfectly fine. We're just using specific characters from the stickers in order to build the target string. But the catch is that if it is possible to do this, we want to return the minimum number of stickers that are needed to spell this target. So that's what makes this challenging. And it might not actually be possible, right? Maybe our target string contains A, Z, right? Maybe some of our stickers have the letter A, but maybe none of the stickers have the letter Z. In that case, it would be impossible using the stickers to create the target string, in which case we're going to return -1. So let's start with the brute force approach, and then I'm going to show you how you can use memoization. And we're actually going to need to be modifying the brute force approach. The brute force is not enough. We're going to have to modify it a lot to even get the memoization approach. And we're going to be analyzing the time complexity as we go, because that's going to be really important for us to actually pass this problem on Leetcode. So the first idea, the most brute force approach that you might come up with is let's just go character by character. So T is our target string. These are our stickers. So we want to be able to build this. So let's just build it character by character. Okay, first character, we need a T, right? So what possible decisions in this case can we make? Well, we can, right as of now, we don't have any stickers chosen, right? The number of stickers we have so far is 0. We want to see if we can build this string. So let's just try every single sticker in one of these paths, right? So if we choose the sticker with, we're going to see, we want to know, does this sticker contain the letter T, because that's the first character that we're looking for. And how are we going to do that? I mean, we could just scan through the entire string, but a more easy way would be to use a hash map where basically for each of the characters, we're going to count how many occurrences it has in the sticker. And we're going to be maintaining a hash map, which basically tells us what characters are available to us based on all of the stickers we have chosen up until this point and the characters from the stickers that we've used. So for example, we start out with, but we know we need to use a T. So what we're going to do from the sticker is basically remove the T, and we're going to be removing it in our hash map, not from the string itself. I'm not actually going to be drawing the hash map because this drawing is going to get really complex really fast if I do, but just assume that we're using hash maps for these stickers under the hood. So first character we wanted was a T, right? Okay, we got that. Great. Now next character we still have some characters available to us from the sticker we chose. Now we don't have to use all of these, but if some of them become useful, why not use them, right? We want to minimize the number of stickers we use. Next character we see is an H, right? So do we have an H available to us? Yes, we do. So let's use that H, and we have gotten 2 characters so far. Next character we have is an E. Now we don't have an E in this word, right? So what we're going to do once again is do a 3-way decision, one for each of the stickers, right? Because what we're looking for now is an E. We're basically brute forcing this, and we want to see if any of the stickers is going to give us an E. Now, of course, with doesn't have any E's at all, right? So once we go down this path, what we're going to find is, okay, we went down this path, we're looking for an E, we still don't have one. So we're just not going to choose that, right? And in reality, in the code, we're not even going to be going down this path in the first place, because we're only going to be going down paths that actually yield us the character that we're looking for. For example, take a look at example, no pun intended, but so this word example, right? Originally, when we chose this word, we were looking for the character T. Does this even have the character T? It does not. It doesn't have a single occurrence. So we're actually not going to be going down this decision at all. And similar with this, science does not contain a T, so therefore we're not going to be going down this path either. So this kind of makes it simple for us. For the first sticker we can choose, it's the only one. And next, of course, we're looking for a sticker that contains the character E, and we know we have two stickers that do contain the character E, example and science. So let's find out which one of these paths is going to lead us to the minimum number of stickers we actually need. So now let's try out these two paths. And the thing to note here is, yes, down this path, we have these characters from the word example available to us, but we also have the characters that were previously unused available to us too. So if any of these characters come in handy later on, we can still use them. But so right now, take a look. We were looking for the character E over here, right? And did we find one? Yes. Now we can basically cross out one of these E's, and that tells us, yes, we have found the E in the word. Next character we're looking for is H, and it looks like we don't have the character H available to us. So once again, we're going to have to go down a decision. Now we're going to end up trying all three of these words, and we're going to check, well, of course, these two don't have the character H, only with has the character H. So that's going to be the only successful path that we're actually going to have. So now to our available set of characters, we have added these four characters. By choosing this sticker, we have added these characters, but we've also increased the number of stickers we've used up until now. Now we've added 3 different stickers. Of course, we are allowed to reuse the same sticker twice. So we were looking for an H character. Here's our H, so let's get rid of it, and let's move to the next character. Now we need an A character. Do we have any A's available to us? Not in this sticker, not in this sticker, but we do have some in the example sticker. So let's cross out one of the A's, and basically that's going to count for the A. Next, we're looking for a T. We don't have any T's available here or here, but we do have one in the second with sticker that we got. So let's cross out this T, and that gives us all the characters in the target string, right? So in this path, we needed 3 different stickers. Now, are there any paths that we didn't actually finish? Of course, these 2 are terminated, right? They didn't work, but this path could possibly lead to a solution. And I'm going to speed through this one so that we don't waste too much time. But when we added this, we were looking for the character E. So this does contain a character E. So we'll cross out one of the E's. Next, we're going to look for H. So again, we would have to use the word with to find the H. So then we could cross out one of these H's. Then we'd look for A. Now, A is not available here or here or here. So therefore, we need another sticker. And that's the only sticker that we have that has the character A is example. So already you can see this path is actually going to lead to 4 stickers to create the target string. So that's definitely not the minimum. So what we originally found in this path was the minimum. It took us 3 different stickers. So now your first thought might be, how can you use caching or dynamic programming to maybe speed up the solution? Because let's analyze the complexity as of now. So clearly we have a decision tree, right? How many different decisions can we possibly make? Well, it's going to depend on the number of stickers. Let's say that happens to be M, right? Now, what's the height of our decision tree going to be? Well, of course, we could possibly, each level could be for a separate character, right? Maybe we need a new sticker for each character in the string. Let's say the length of the target string is n. So basically, the number of nodes or values in this decision tree is going to be m to the power of n. So that's not very efficient. So if we had something like maybe 2 to the power of n, that'd be okay. Like that'd at least be a start. But m to the power of n, that's very inefficient. M could be anything, right? As of now, it's 3. And believe it or not, the difference between 3 to the power of n and 2 to the power of n is a massive, massive difference. And not only that, we know it could actually be like maybe 5 to the power of n or higher, right? That's going to be really complex. So we have to try to see any way we can make this better. And what I'm going to be targeting actually is the solution that's roughly 2 to the power of n. Now, there is going to be another constant, for example, n times 2 to the power of n, but clearly in a solution like this, the n is not going to be the significant factor. 2 to the power of n is much, much higher, and this is going to be much better than something like 3 to the power of n. So the main reason we can't really use caching in this problem is because let's say we get to this point, right? And let's say we've done the first 3 characters of the hat, right? We were trying to create the hat, and let's say at this point, we've already gotten the first 3 characters, so we're only looking for this. You might say, okay, can we just use this target string in our cache? And you could try that, but you would be wrong. The reason is we can't simply use this as the key value in our cache because we also have to keep track of what characters are actually available to us. Because remember, based on our previous decisions, we still have these characters available, these, right? And if maybe we got to the same point in this decision, right? We're only trying to create hat, right? These 3 characters. Well, it's still going to be a different result because we have different characters available to us if we went down this decision. So we can't just use the target string to cache. That would be nice, but we can't. So what I'm going to show you is a way where we can use the target string. So we are still going to have decisions like this. Our decision tree, the structure is mainly going to be the same, but we are going to use cache. Now, of course, we still aren't going to go down these paths because we're going to see that they don't contain the first character. So we're not going to go down either of these paths. So let's still start with this one. What we are going to be doing down this path is going through character by character in this string, similar to what we did before. So first, we're going to look at the character T. Do we have a T in here? Yes, we do. Let's get rid of it so that we can cross this T out. Next, we're going to get to the character H. So do we have an H? Yes. Cross it out. Cross this one out. Next, we're going to look at the character E. Do we have an E? Nope. So that's going to be remaining, right? We need to find an E somewhere, right? We need to get a word to find an E somewhere, but we're not going to stop there, right? Before we were saying, okay, now let's create the rest of this substring. No, we're going to be greedy. We're going to exhaust every possible character that's available to us and see if any of these remaining characters can possibly fit in here somewhere. And you'll see why I'm doing that in a moment. So do we have an H available to us in our stickers? Nope. Do we have an A available to us in our stickers? Nope. Do we have a T available to us in our stickers? Nope. So what does that tell us? We still have to find these 4 characters E hat, right? But before what we were saying is we're still keeping track of these remaining characters that are available to us because they might be useful somewhere. But what we just found out is these characters are useless. They don't fit in anywhere in this string. It could have been possible maybe a W would have fit in at the end, for example, or maybe even in the middle, and we could have crossed it out, and then we'd have this remaining portion left. See how the remaining portion possibly might not be a continuous substring. It's basically going to be a subsequence. How many different subsequences of this string could we have? Let's say the length is n. We could have possibly 2 to the n different subsequences. That's what we're going to be using in our caching solution. But let me continue for now. So what I'm actually going to say is, since these are useless, I'm not even going to keep track of them. Yeah, we didn't use them, but I'm just crossing them out anyway. Let's make things simple for us. And right now, we're looking for an E character, right? So let's choose all stickers that have an E character available to us. We have 2, example and science. Now we know from previously running through the example that this is not going to lead us to the solution, so I'm going to mainly focus on this one to not make the drawing too messy. But so once again, what we're going to be doing, I'm using a different color because we already used red. So we're going to be going character by character. We're going to start at the E. Do we have an E available to us? Yes, we do. Let's get rid of an E, and then we can cross this E out. Next, we're looking for an H. Do we have an H available to us? Nope. So before, what we did is we said, okay, let's stop there and just try a different string. Nope. We're not going to stop. We're going to exhaust every possible character we have available to us. Once we've done that, then we can stop worrying about this entire sticker. So we couldn't find an H, but let's try if we can find an A. That's the next character available. So can we find an A in our stickers? Yes, we have an A in example. Let's get rid of it. Therefore, we can cross this A out. Next, we're looking for a T. Do we have a T available to us here? Nope. So therefore, we went through every single character here. A couple of these were useful, but the rest of them are useless, right? We don't care about them. Get rid of all of them. We're not going to keep track of this. And the next character you can see that we need in here. So before we had E hat, right? Over here, we were looking for E hat. Now we're just looking for HT, right? Even though HT is not contiguous in this target string, this is basically the characters remaining that we're looking for. In other words, this is a subsequence of the target string. So which one of these stickers has an H available? Only a single one with. So now let's run through the with. So let's start at the first character. It's an H, right? Do we have an H available to us? Yep, we have this H. Last character, do we have a T available to us? Yes, we do. It's in this. So get rid of that. And now we have actually found the entire target string, right? Same as the previous result, we needed 3 total stickers. But the difference with this solution is we can actually use it in our cache. Let me tell you why. Notice how now we're not actually maintaining a previous list of stickers that we can still use in our solution at this point in time, right? We basically cross out the previous stickers. We say this most recent sticker is the only relevant one. And initially we started with the initial problem of the hat, right? Then we got to a sub problem of E hat. Right now we're looking for the minimum number of stickers it takes to create this subsequence E hat. Now down this path, we found it took 2 stickers. Down this path in the previous drawing, we saw that it took 3 stickers. So we are still gonna go down both of these. We're gonna say, okay, what was the minimum? It was 2, right? So then we're gonna cache that. We're gonna say, okay, to create this substring E hat, it took 2 stickers. We can cache that. Now in this problem, since it's a pretty small decision tree, it's not really going to be helpful, but it could have been possible that, down a few paths, right? It could have been a really large decision tree, right? Maybe we repeated the problem of E hat, right? Maybe we come back here and we say, okay, what's the minimum number of stickers it takes to create E hat? Now we would have that in our cache. So we could immediately return 2, right? We know for sure it takes 2 stickers. These are the 2 stickers it takes, and it won't depend on any previous stickers that we chose, because every time we choose a sticker, we're exhausting it as much as we can. And as I mentioned before, what's the total? It's true that this entire tree, in theory, could have been really complex. It could have been m to the power of n, where m is the number of stickers. But now, since we're caching, we know for sure that there's only going to be 2 to the power of n different subsequences of the target string, where n is the size of that target string. So that's what's going to be cached. Now, technically, for each one of these nodes in this tree, we are still going to be running through the entire target string, just like I showed you, right? Since we're exhausting every single sticker, we have to run through the entire target string. So it's actually going to be 2 to the power of n multiplied by n, but that's not so bad compared to m to the power of n. So this is the main idea. Now I'm going to jump into the code, and believe it or not, the code is still pretty complicated, even knowing all of these things. Okay, so now let's get into the code. The first thing I want to do is convert each sticker to a hash map where we're converting the sticker to the count of its characters. I'm going to call that stick count. So we're going to go through every single sticker in stickers. I'm using enumerate so we can get the index at the same time. So what we're going to say is to stick count, since it's a list, we're going to append an empty hash map, an empty dictionary, and then we're just going to go through every single character in this sticker. And we're going to say, okay, stick count at index I, which is going to be a hash map. And then we're going to say, okay, for this character, let's increase the count by 1. So 1 plus stick count. And you could use a library function to basically get rid of these few lines of code. But in interviews, I'd expect they would want you to actually write it out. So we're also going to have a DP dictionary before we actually get into the recursive portion. So we're going to say the key is going to be a subsequence of the target string, and the value is going to be the minimum number of stickers it takes to create that target string. So this should give you a general outline of, how we're going to be actually caching and getting the time complexity of this problem. So next, we're going to use DFS, our recursive function, to actually get the decision tree. So what we're going to be passing into this is T for the target string that we're trying to build. In some cases, it's going to be a subsequence of the target string. We're also going to be maintaining one variable called stick, short for sticker, basically whatever sticker we are currently using to build this target string. Remember, we're only going to be keeping track of one sticker at a time because we're going to take this sticker and exhaust it. Now, one base case is going to be if the target string is already cached, is already in our DP, in which case, of course, we're just going to return DP of T. Now, another base case would be if T happened to be equal to the empty string, in which case we would return 0, meaning it just took 0 stickers for us to do it. But we actually don't need that, and you'll see why when I actually finish the rest of this function. Now, let me show you how we're actually going to be calling this DFS function before I continue, just so you actually know that. What we're going to do is we're going to call DFS, right? What we're going to do is we're going to pass the target string in, and initially we don't know what the first sticker we're actually going to choose. So we're actually just going to pass in an empty dictionary to indicate we have not actually passed in a sticker yet. We'll decide which stickers to use when we're actually inside of this function. And from this, we're going to return whatever was the minimum number of stickers, right? That's the result. Now, after that, we're of course just going to return the result. That's going to be the return value of this entire function. But what if result equals infinity, right? So we're gonna first check if result does not equal infinity, because that's the default return value I'm going to define in this DFS function. So if it's not infinity, then return result. If it is infinity, remember what we actually want to return is -1. Infinity basically means we were not able to create the target string. So now that you know this DFS function, we could pass in a sticker or we could pass in an empty hash map, meaning we didn't pass in a sticker. So what we're going to keep track of is the number of stickers we used, or in other words, what's the result so far? It's going to be 1 if sticker is non-empty, else we're going to start our result at 0, meaning we didn't get past any sticker, so we haven't used any stickers so far. Next, what we're going to do is we're going to get to the part where we actually exhaust the sticker that we passed in. So what we're going to do is we're going to go through every single character in T. We're going to check if this character is in stickers and if the count of that character, stick of C, is greater than 0, meaning it has at least one occurrence of it. So then what we're going to do is basically say, okay, we used one character from this sticker, so let's just decrement the count by 1. Else case is if we did not find this character, right? So what we have to do is keep track of the subsequence. Remember, the subsequence is basically what were the remaining characters of target that we weren't able to get. So we need to keep track of another variable. Let's call it remain target. Initially, it's going to be empty, but for every character that we don't find available to us in the sticker that we passed in, what we're going to do is say, okay, remain T plus that character. So now the easy thing would be, okay, after we're done, we can just go ahead and return result, right? If we were able to create the entire target string T with one sticker, then we would return that, right? But now it's possible we still have some characters remaining, right? So if remain T is non-empty, then we have to do the recursive portion of this function. If it is empty, then we can just go ahead and return the result. It just took us one sticker to create this remaining portion of the target string. And we're going to keep track of one variable, let's call it used, and initially we'll define it as float of infinity. Now this used variable is going to keep track of, okay, how many more stickers do we need to complete this remaining portion of the string only? It's possible we were able to get some of the characters, but we do have a remaining portion left. Let's see how many stickers it takes to create it. And this is the part where we're going to go through our decision. So what we're going to do is we're going to go through every single every single sticker in the list of sticker hash maps that we defined outside over here, right? That was the first thing we did. So we're going to go through every single one of those stickers, and we're going to do the recursive case now. But remember, we only want to do the recursive case if this sticker at least has the first character that is remaining in here. So what we're going to do, just to keep the code clean, is say if remain T, the first character in remain T, is not in S, that means this sticker doesn't even have the first character in the string that we're trying to create, in which case we're just going to skip this sticker altogether. Now, if it does have the first character, that's when we're actually going to be doing the recursive case. So let's do the DFS. What are we going to pass in? Of course, we have to pass in the remaining target string that we're trying to build, and we're going to pass in S. S is the sticker that we're actually going to be using this time around. And of course, we're keeping track of how many stickers we used to create this remaining T string, and we want to minimize that. So we can say used is going to be equal to the minimum of itself and the return value of this DFS. And one last thing, since we're passing in the sticker to this function, and notice how in the function, we're actually taking that sticker and modifying it, right? We're decrementing it. And a sticker is an object. It's basically the count of characters in each sticker. We don't want to permanently modify it in case we have to reuse the sticker multiple times. So what we're going to do is actually create a copy of that sticker. Now you might think that's not super efficient, but in the context of a problem like this, where the time complexity is exponential, this is not really going to be the limiting factor. So once we've gone through this entire loop, what we can say is for this remaining string t, remain t, we went through every single sticker and we tried to find the minimum. So by now we have found the minimum. So this is the part where we're going to cache it. We can say for remain t, we have found the minimum number of stickers it takes. So we'll store that as used. Now also, don't forget, we need to return the result. So let's say, initially we used 1 sticker right up here. Result was initially 1. Maybe it took us, let's say, 3 more stickers to do the remaining portion of t. So then what we would say is result is going to be equal to the result. We're going to be adding the extra number of used stickers that we just used. And then outside here is when we're going to be returning the result. Now in some functions, notice how we defined used as infinity. It's possible used stayed as infinity. So this might actually cause an overflow error in some languages. So you might want to be careful about that if you're using a different language. But in this case, it doesn't actually cause an overflow. And so, yeah, so it might have been possible. Maybe we passed in 1 sticker and 1 sticker was enough, right? We were able to create the entire target string in 1 sticker, then we would return that. Maybe we had a remaining portion of the target string and it took us a few more stickers to do that. In that case, we would take those extra stickers, add them to the result, and then return the result. Either way, we are still returning the result. And here is the part where you can see that we are doing the caching portion of this problem. And then we would detect the cache up here. Now, what happens if we passed in an empty target string t? Well, this entire loop would be skipped, this if statement would be skipped, and then we would just return the result, and it would be 1 or 0 depending on if we actually used the sticker or not. So this is the entire code in all of its glory. You can see that it does pass this problem, even though it's not very efficient. It is an exponential solution, and there are some solutions that have a better runtime. And if you're still confused by this problem, I really don't blame you. This actually took me a long while to even get my head around this solution itself and even come up with this one at all. But I hope that this was at least a little bit helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon and hopefully some easier dynamic programming problems.